Hey guys, so today we'll be doing something called something with the subheading stellar radii, and stellar radii is basically another term for the radius of a star, right? So we'll be talking about how we can find out the radius of a star. So stellar radii is another term for radius of a star, right? So there are three steps. I'll write down the three steps. Assume star as a black body. Number two, Wien's displacement, and we'll talk about each step separately, so don't be worried about that. Wien's displacement. Number three, Stefan Boltzmann Law. So you just remember this order and you can easily find out the radius of a star. So now let's talk about what is meant by the term black body. Number one, black body. Now the black body is a theoretical object that absorbs all radiation falling on it. Hence it would act as a perfect emitter at specific temperatures, right? So I can write this down. Theoretical objects that absorb all radiation falling, sorry, a better term would be incident on them. Hence they behave as perfect emitters at specific temperatures, right? So this is only done so that calculations can be done easily. So this is for the ease of us, for the ease of us who are trying to calculate the radius of a star, right? So stars are not actually in real time, they're not fully black bodies, but we consider them to be black bodies so that we can calculate the radius easily. So, and that radius is an approximate. It's not very accurate, right? So now it says at specific temperatures, right? So what happens is that, for example, this is a star and there are radiations falling on it, right? It absorbs all the radiations and reflects nothing back. So the color we see is black because it's absorbing all the radiation and it's not reflecting any wavelengths of any sorts, right? Now what happens is when the temperature of the black body goes up, when the temperature, for example, the temperature goes up to, for example, 5000 Kelvin, now it will be emitting wavelengths because the temperature went up, right? So now, for example, we'll see the color red. So this is what happens with the black body. So we need to know about a specific graph, and the graph is intensity against wavelength. Now this is an intensity against wavelength graph. intensity, wavelength, right? Now the graph would be similar for all black bodies, and the graph would go like, if you're a biology student, you're probably familiar with a enzyme denaturation curve, and this is very similar to that. So this peak I'm marking, this is the wavelength emitted at maximum intensity, and this is also the spot where the temperature of where the surface temperature of the star is the highest. For example, this is 6000 Kelvin, this could be 4000 Kelvin, these are just examples. 4000 Kelvin, this could be 3000 Kelvin. So the wavelength emitted at the peak is when the star has maximum temperature, and this wavelength is emitted with maximum intensity. And for example, this wavelength has the value of 500 nanometer, and this is, we call this wavelength max, right? This will make sense when we talk about Wien's displacement law. So from this graph we have to understand two main things. First of all we see the peak, and then we see what x value this corresponds with, and then we call that x value wavelength max, right? And then we note this wavelength max value, and then we go on to step 2. Step 2 is the Wien's displacement law. Now this will make sense. You'll see why we use the wavelength max value. So we'll use Wien's displacement law. So we're done with step 1. The step 1 is basically figuring out wavelength max, and wavelength max is the x value for when the y value is maximum for the graph, right? So the y value being maximum intensity, and the x value corresponds with that value, and hence that x value is wavelength max. Now the Wien's displacement formula you'll have to memorize, and you need to memorize the constant as well. The constant is given in the exams mostly, but to be on the safe side you should remember it. So the Wien's displacement formula is T is equals to 2.9 into 10 raised power minus 3. The units for this constant are meter Kelvin, and upon wavelength max. Now this is the wavelength we found from step 1, right? T being the temperature, wavelength max being wavelength in meters, and 2.9 to 10 raised power minus 3 is a constant, right? Now for example, the wavelength max value we found right here was 500 nanometer, right? So what we can do is we can input this value. We can input this value, T is equals to 2.9 into 10 raised power minus 3 upon 500, and because it's nano we need to convert it to meters. 500 into 10 raised power minus 9, right? And then we can solve for T. T can be any value you find here. I don't have a calculator near me, so I'm sorry for that. So this is Wien's displacement law, and now we move on to the third step. Now we have a specific temperature, right? We have a specific temperature. For example, we can give it a value 2000 Kelvin, and this is not the value I found, this is just a value I'm considering as an example, 2000 Kelvin, right? Now we move on to the third rule, to the third step. The third step is Stefan Boltzmann's law. Stefan Boltzmann's law, right? Now what we do is that we use the formula for Stefan Boltzmann's law. We need to remember this formula as well, and the constant too. So the formula is L is equals to 5.67. This is the constant, the Stefan Boltzmann constant, into 10 raised power minus 8 into A into T to the power 4, right? So L here is the luminosity. L is the luminosity. A is the area of the star area, and T is the surface temperature that we found in the previous step. Surface temp. Now we're considering T as T is equals to 2000. So we can find out the T value from step 2 using the wavelength max value from step 1. So now you can see how these steps are all connected, right? So you will be given the luminosity. You can input the luminosity. For example, luminosity is the value for luminosity given is 20 is equals to the constant. I'll write K for constant. The value for the constant is given as 5.67 into 10 raised power minus 8. You'll need to remember this constant value. And we replace A, the star area, with 4 pi r squared, right? Because the area for a sphere is 4 pi r square, right? And we replace T with the temperature from step 2, which was 2000 to the power 4, and then we can solve for R. And the value for the constant is 5.67 to 10 raised power minus 8. We can put in this value and we can find R. R can be value we can consider is 1000 meters. And this is, again, I have not calculated this value, but you can calculate it on your own using a calculator. I do not have one near me right now, I'm sorry. So this is how you can find this radius of a star. But in the exam there are many questions from other exam boards where there comes a different question regarding step 2. So I'll show you the question. I'll show you an example of a question that comes. So they'll say the surface temperature of a star is 5000 Kelvin. Its wavelength max value is 500 Newton meter. Another star has wavelength max 250 Newton meter. Find the surface temperature for this star. Now they've given us 2 stars and they've given us the temperature for one and the wavelength max for one. So temperature for one and the wavelength max for one, and they've given us another star with a wavelength max of 250 Newton meter, and they've asked us to find the temperature. So again, we'll make 2 equations. We'll use the Wien's displacement law. So we're not finding the radius, but we're finding the temperature. So we'll use the Wien's displacement law, which goes like T is equals to 2.9 into 10 raised power minus 3 upon wavelength max. So we'll call one of the stars star 1, and the other star, star 2. So the equation for star 1 would be 5000 Kelvin multiplied by 500 nanometer. So we took the wavelength maximum value on this side is equals to the constant k. I'm writing the constant as k, and for the other star we were given the wavelength max as 250, and we're not given the temperature. So I'll write down temperature as T and wavelength max as 250 is equals to k, right? So both equations equate to the value k, hence we can equate both equations because they equal the same thing. So we can write 5000 into 500, and we don't need to convert nanometer to meter in this example because both wavelengths are given in nanometer. If one of them was in nanometer, we should have converted it to meters. So 5000 into 500 is equals to T into 250. We can multiply 5000 into 500 upon 250 is equals to T, and we can find out the value of T. I'll just grab my calculator on my phone. 5000 into 500 divided by 250 would be 10,000 Kelvin, right? So this is something very important, and this is something you need to know because this does come in exams. So an easier way to do this question would be that you do, if instead of making two equations like these, you can just equate them directly because you know that they equate to the same thing. So you can just write 5000 into 500 is equals to 250 into T. So you can formulate a formula. The formula would be T1 into wavelength max 1 is equals to T2 into wavelength max 2. So this is the formula you can use, and you need to use this formula when two stars are given. So when two stars are given, you need to compare them and you use this formula. But if only one star is given, you just use the Wien's displacement law. If only one star is given, you use this. If two stars are given, you use this. So that was all for today. We learned how to find the radius of a star. There are three main steps to finding the radius. First, assuming it's a black body. Number two, using the Wien's displacement law. And number three, Stefan Boltzmann law. And another thing we discussed was finding the surface temperature of a star using the Wien's displacement formula. But if two stars are given, we equate them and we use this formula instead. So that was all for today. Thank you very much for watching. Don't forget to like, share and subscribe. Hope to see you in the next video. Bye bye.